About life? No. Now, let's talk about like a couple of problems, one of them being 17. Okay? So, here's the car. It's initially going about 40 kilometers per hour. Something like that. Okay? And you're hit the brakes, right? And it's going to come to a stop. So one of the first things you have to figure out is what's your original velocity and what's the final velocity. Okay? Because if you got that screwed up, everything else is going to go wrong. Okay? So V naught, think of that O on the V naught as being the original. Okay? So this thing was originally going 40 kilometers per hour. So it's the first thing you're going to have to do with the kilometers per hour.
Convert it.
Change that into meters per second. You have to be able to do that without giving it a second thought. Okay? You have to be able to do that. So, here's the grand idea. And if you're really going to understand these problems, you have to work them beyond just an equation. Okay, you have to look at the grand scheme of things. So, actually it's going to 20 kilometers per hour, not 40. It's going to 20. So, here's the velocity time graph. Okay, 20 kilometers per hour is about 6 meters per second in round numbers. Okay, so we're going from 6 meters per second, and we're going to come down here like this to 0. And you're told it stops in 3 meters. Okay. 3 meters is about 3 long strides. Okay, so it isn't that far. Okay? Now, here's the whole key. The next thing you know, you're going to be going 40 kilometers per hour, and you're going to stop with the same acceleration. Now, here's where this turns into a big picture. If you're going 40, which puts you up here at about 12, when that thing stops, because it stops with the same acceleration, what's that line going to look like relative to the first line?
Same.
Yeah, it's going to be parallel with it because it's going to have the exact same acceleration. Now, here's what you could do. You could sit there and go, well, this is easy. If I'm going about 6 meters per second, and I stop in 3 meters, if I'm going twice as fast, which is what I'm doing, then it should take twice the distance to stop. Right? That's one thing you could do. Okay? You could go, well, if I'm going 6, I stop in 3. If I'm going 12, I'm going twice as fast. That should take twice as far to stop. Okay? And sometimes in physics, things are a simple ratio like this. This isn't one of them, by the way. Okay? This is not one of them. So, what are you missing out of this deal? What do you not have? Time. Because if you think about every problem, you only have 4 possible variables to worry about. Okay? Literally, you only have 4 possible variables. You can worry about V naught, acceleration, there's 5, time, and distance. These are the only 5 variables that you ever have to worry about in any problem. Okay? Literally, these are it. Only 5. And you basically only have 4 possible equations. So it isn't like you have 1,000 equations from which to choose. You only have 4. Okay, literally, every problem that you're going to do is some variation on those equations and some combination of these. So as soon as you don't see time, the only thing you have left is v squared equals v naught squared plus 2ax. Okay, that's the only thing that you have left in town. That's it, nothing else. So, now, if you're going to do this, as Brecken will attest, these things are squared. Okay? You have to square the numbers. And again, look at the big picture. When on this situation, what has to be the sign of my acceleration? Positive or negative? Negative, because I'm slowing down with positive velocity. So if I do this calculation and I don't get an acceleration that's negative, I've done something wrong. Okay, because if you end up with a positive acceleration, you're saying that you're starting here on this velocity time graph, it's going to go up like this. So you're going to be going up like this, but yet you're going to stop? Wow, that's cool. No, won't happen. Okay? Won't happen. So you're going to get an acceleration out of this equation. You know the final velocity, the initial velocity, and the distance, you can get an acceleration. Then you're going to use this same equation a second time, now that you know the acceleration, to calculate the distance that it's going to take to stop. And so that distance that it takes to stop should be somewhere between 10 and 15 meters. Got a head nod for that, Katie? Okay, life's good. Life's good. Now, 20 is a similar type deal. Okay? 20 is a similar type approach. You got a VW Rabbit, which is a horrible, ugly car. It really was. You can go from rest to 50 miles an hour in 8.2 seconds, which is actually, for acceleration on a car, is pretty bad. Okay? And that's if you're like really pushing. All right? So then it says, how long will it take to speed from 48.3 to 64.4 along a straight run if the acceleration is the same as the one that's going from rest to 80.5? Okay, so here's the basic idea. And again, look at this on the velocity time graph standpoint. You're going, okay, here's my velocity time. I'm going to go from 0 to whatever, 80.5 in 8.2 seconds. Okay? So that's easy. I find the acceleration. Boom. There you go. Okay? Now, the whole key to this, then I say, all right, how long is it going to take to go from 48.3 if I'm going to use the same acceleration? So in other words, this line is going to have the exact same slope. I got to figure out how long it's going to take to go between these two different velocities using that exact same acceleration. Okay? So basically, you use the initial to figure out the slope, and then you say, okay, well, how long is it going to take to go in between those 2 points with the exact same acceleration? Okay? That's the grand scheme of things. Now, let's talk, because I want to point this out, or otherwise I'm going to end up with potentially weird answers. Let's talk about number 11 for just a second. Okay? So, gal's running along. Okay? She's going to slide in. Velocity time graph. Make sure that you have labeled everything on that velocity time graph. Okay? Make sure that you have done everything that you need to have on that velocity time graph. And then on C, and here's the most important thing, I want to know how fast was she moving at 0.3 seconds into the slide. So here's what's happening. Here's the base, okay? She comes in, boom, okay, gonna slide, right? No worries there. Initially, she's going 4 meters per second, okay? And she's going to come to a rest. Your velocity time graph is going to look something like this. There's 4 meters per second. There's 0.5. I want to know what's happening at 0.3. Okay? Now, so here we are at 4 meters per second. We're slowing down. At 0.5, we've stopped. I want to know how fast she's going at 0.3. Now, could, okay, I don't want to know if it is, but here's the question. At 0.3 seconds, could my velocity be a negative number? Aubrey, you shake your head no. Why?
Because if by the time it gets to 0, it's at 0.5. So like you can't, like it's just going down, it hasn't crossed the x-axis.
Yeah, number one, I haven't crossed the x-axis, okay? Physically, what would it mean if you say that she has a negative velocity at 0.3 seconds?
She would have turned around.
Yeah, so you're going to say she's going to come in here and slide into second base, going in this direction, but at 0.3 she's going in the opposite direction, But yet, at 0.5 seconds, she ends up at second base. Cool, not going to happen. Okay? So there is no way your velocity at 0.3 seconds can be a negative number. Okay? It's physically impossible. It's mathematically impossible. It's just impossible. Depending on how you, no matter how you cut it, it's impossible to happen. Okay? But it should be somewhere, but your answer has to be somewhere between 4 and 0. Okay?
This is the example.
And again, here's the big picture. This is just a slope intercept. All I want to know is what is the value of the velocity at 0.3 seconds. So it's just v equals v naught plus at. You know the acceleration, you know the time, you know the initial velocity, find the value of v. So all I'm trying to find is the corresponding value of velocity that matches up with that corresponding value of time. That's all I'm trying to find. Okay? That's it, nothing else. On the vector diagrams, make sure that you have labeled them velocity or acceleration. Okay? Don't make me guess which is which. And if you want those velocity vectors to get smaller, clearly show them getting smaller. If you want the velocity vectors to get bigger, clearly show me the velocity vectors getting bigger. Okay? All right. Anything else? Are we good?
So,
Life's good? Your answer to number 20, by the way, that time should be somewhere between 0 and 3 seconds.
yeah. Want me to turn this on?
All right, kids, so here's the next big thing, and that is gravity. Now, gravity is one of those things that you've experienced for quite a while, basically since you've been on this earth, okay? And there are a couple of things that are kind of mystifying about gravity. If you look at like the great mysteries that we still have yet to really explain, gravity is one of them. We know the effects of it. We know it holds us in orbit around the Earth. It holds us on the Earth. You know, it holds entire galaxies together, okay? But we really don't know how it works. We see the effects of it, but we're still a little fuzzy on the actual mechanism. One idea is that gravity is caused by particles called, wait for it, gravitons. Okay, you've heard of like electrons, protons, neutrons. So they think that gravity is carried by a particle called a graviton. It's a catchy name. Okay, I see gravitons. Really? Okay. So, but we really don't know like where they are or where they emanate or how they interact. It's a little fuzzy. Newton tried to explain it. He came up with math. Einstein did it. He used space-time warping, which we'll talk about when we get into gravitational fields. But for now, all we need to worry about is the fact that gravity causes an acceleration. Now, one of the things that on my pet peeve of things that irritate me, don't tell me that, oh, gravity is negative 9.8, okay? This is the acceleration caused by our gravitational field when I drop something. This is not gravity, okay? It's the acceleration caused by gravity. But negative 9.8 is not gravity. So when I ask you, well, what do you know about the problem? I'll say, well, I know gravity is negative 9.8. I will banish you from my presence at that point, okay? You can say, well, gravity causes this acceleration. Okay, cool. That I can live with. Now, when you look at gravity problems, there's two basic ideas. One is that you just hold something up, and this is what we're going to start with, and we're just going to drop it, okay? Situation number two, I take the same golf ball, I throw it up in the air, and then it comes back down. So those are basically the two ideas, right? I can either throw it up in the air, or I can just hold it up and I can drop it. Now, here's what's going to be common. There are certain things that are common to both of these. No matter what, anything going up, velocity, acceleration, position, whatever, is going to be defined as being a positive number. Anything going down is going to be a negative number. So you can think of it like your bank account. If your bank account is moving in the upward direction, hey, that's a positive thing. If your bank account is moving downward, oh, that's a negative thing. Okay? Unless you buy something really cool and then it kind of balances out. But generally, bank accounts that are going down are negative things. In both situations, this gravitational acceleration is going to be negative 9.8 meters per second squared. That way you don't have to think, oh, do I make it positive? Do I make it negative? Ooh, I don't know. Oh, okay. G is always going to be negative 9.8 meters per second squared. If I drop it, and this is going to be important, if I just drop it, my initial velocity is going to be zero because I'm just dropping. Okay, it doesn't have any velocity to start with. If I throw it, especially if I throw it up in the air, it's going to start with a positive velocity. Okay? Now, this could be a negative number. If I hold something up and then I throw it down, this could be a negative number, but we'll deal with that later. Okay? When you throw something up in the air, and this is going to make life very simple, anytime you reach a maximum height, your velocity immediately is zero. So when this thing is going to reach its maximum height, the velocity goes to zero. Why does it go to zero?
Because it doesn't move. It doesn't change its direction.
It's going to change the direction, right? So it has to slow down, stop, and change direction. So this is a little nugget to always keep in mind. When something reaches maximum height, the velocity momentarily goes to zero. And in both situations, we're going to define the ground as being zero. Okay? So where you lease it, or wherever you shoot it up, boom, that's going to be zero. Okay? Got it? Good? Great. So let's talk some numbers. So let's say that I'm going to hold this golf ball up to a height of 2 meters. Okay? I'm going to drop it. So this thing is going to be 2 meters high. And I'm going to drop it. So I want to figure out how long it's going to be in the air. And then I want to figure out what's the velocity when it hits the ground. So at that very instant that the ball comes in contact with the ground, I want to know how fast it's going. So before we do any calculations at all, I don't even want to worry about equations for now. I don't care about the equations. We'll deal with them later. I want to start with my velocity time graph. So here's my velocity time graph. Where is it going to start? At 2?
No.
Big difference between 2 and 0.
It's going to start at 0.
So we start at 0. Okay? And what's it going to do? It's either going to go up or it's going to go down.
Down.
Down?
Down.
Go up.
Down.
Ground's a reference point. That's 0.
Down. Down, 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 down.
Down?
Yes. At a constant rate of negative 9.8.
And what's the slope of the line going to be?
9.8 meters per second.
Well, it's going to be 9.8.
Negative
Negative
9.8.
9.8.
You know what I mean.
Okay? True? Okay? Now, got it? That was close? Yeah. Gravity storm. Whoa! All right. So, here's going to be the slope of the line. Now, let's think this through. What if I let the ball fall for exactly 1 second? If the ball falls for exactly 1 second, how fast is it going to be going at the end of 1 second? Negative 9.8. Right? Meters per second. If it falls for 2 seconds, it's going to be traveling twice that, which would be about negative 19.6. So this just tells me how fast this thing's, the rate at which the velocity is going to change. That's all that means. Okay. So I got this. It's going to start at 0. Boom. There we go. At any point, if I know the time, I can figure out how far it falls because of the fact that I can find the area of a triangle, right? So if I know how long it's in the air, I can use this to figure out how far it falls, okay? Now, but here's going to be something that's important. When I look at this velocity time graph, right away, what's the sign of my final velocity going to be?
Negative.
Negative. So I know I'm going to land with a negative velocity because I'm always defining down as being negative. So I know I have to land with a negative velocity. So when I multiply, this is going to be important, when I multiply my positive time by my negative velocity, what's the sign of my displacement?
Negative.
Negative, right? Negative? Okay? So my displacement's going to be a negative number. But you're going, well, hold on, Mr. Burkett. You said the ball fell 2 meters. But my displacement has to be a negative number. But here's the trick. Okay, it really isn't a trick. This is a logic situation. When the ball lands, what's its final position? 0. Okay? 0 meters. What's my initial position? 2 meters. Right? How do you calculate displacement? Final minus position. What's my final position? My initial position is, so if I take 0 minus 2, I get negative 2. So my displacement is a negative 2 meters. Okay? And later on you'll see the importance of this. Now, here's another option that you can do. It works the same way. You could make this point where you let go of it 0. Okay, you can do that. You say, well, I want to make the point of release be 0. Okay, that's cool. You can do that. If I make this 0, then this position down here becomes a negative 2 meters. Okay? But it's still the same thing. If I take final position, negative 2, and subtract my initial position of 0, I still get a displacement of negative 2. So even if you make this 0 and make that negative 2, or if you make that 2 and make that 0, you still end up with a negative displacement, and it's cool and life is great. Okay. So let's talk about time. I need to find a time, and I know an initial velocity, which is 0. I know how far it falls, right? So I know my value of x. I know an acceleration of negative 9.8 meters per second squared. And I'm searching for time. So what will relate initial velocity, acceleration, and distance, and time? What equation? There's only basically 4 to choose from. No. I don't want to use that equation. Because that equation doesn't involve time.
We could do the final velocity plus the initial velocity.
I don't know the final velocity.
No, we don't. You're right.
Bracken? On your equation sheet, there's only 3 to choose from.
The second one.
How about the second one? Why the second one?
It only has the initial velocity.
Yeah, and what's my initial velocity? 0. Oh, well, that's simple. So if I look at that second one, where I go x equals 1/2 at squared plus v naught time, what's my initial velocity? 0. So all of this goes away because my initial velocity is 0. Now, I need to get time by itself. So, what can I do? Multiply by 2 and divide by my acceleration, and that's going to give me my time. Okay? Now, you especially once we get into projectile motion, but here's the golden rule when you're looking at vectors. Basically, for now, we're going to be dealing with like horizontal motion, like a car moving along the ground, or we're going to be dealing with vertical motion, gravity. Here's the golden rule. It's kind of like the ads for Vegas. What happens in the X stays in the X. What happens in the Y stays in the Y. Okay? Nary the two shall meet. They're completely independent of each other. So even though we're talking about X, okay, and X in this case is just a distance, but we're talking about the x representing how far this thing is going to fall. So if you're talking about vertical motion, okay, vertical motion like this, it's going to be how far it falls, and then your acceleration has to be the acceleration caused by gravity. Now, one of the key things that, as we go through this, and you'll hear me talk about this a lot, it's a concept I developed last year, okay? And it's called Jedi, it's kind of the Star Wars theme, Stoffel Law. Okay? Now let me explain what this is. Jedi Stoffel Law is this, and it relates to forces. This stands for stop the force and watch. Okay? You stop the force and you observe what happens to the motion. So, to hold this up, do I have to apply a force to the ball?
No.
Yes.
Oh. Yeah.
I do. I have to apply a force to the ball to hold it up, right? Okay? Now, if I stop applying this force and watch what happens. So I'm going to stop the force that I have acting on the ball. As soon as I stop applying that force, what happens?
Falls.
It moves. It accelerates, right? So that means there has to be another force acting on it. Because visualize this. If I let go of this, and I'm in a zero gravity field, there's no gravity whatsoever. If I stop applying that force and watch what happens, if I can let go of it, what's it going to do? It's just going to stay there, right? Objects actually don't like to accelerate. They're like you guys on a Saturday morning, okay? 6 o'clock on a Saturday morning, okay? You're at rest. You want to remain at rest. If Mom's is going to make you clean the house because Aunt Martha is coming over for breakfast, she's got to apply a force because you want to remain at rest. Same thing is true with this ball. So if I stop applying one force and it begins to accelerate, right away I know there has to be another force acting on it. I take this remote control, right? I give it a push, right? Once I stop applying one force, okay, and I stop applying that force, what does it do? Does it accelerate as soon as I stop pushing it? Yeah, it does. It accelerates. Why? Because it slows down. So if I stop applying a force and watch what happens, if I see any kind of acceleration, that means there has to be another force acting on it. If I stop applying a force and it moves in a straight line, that's another situation which we'll deal with. So that's one of the key things you want to look at. Think this through. Okay, I stop applying one force. What's going to happen after I stop applying that force? If I stop applying this force and let go, I immediately get an acceleration. So we'll talk about this concept a lot. It's an important deal. So here's the deal. So I stopped applying the force. I watched what happened. Hey, I got an acceleration. That means gravity is acting on it. So here's what we're going to do. Now, what I'm going to do is wrong. Okay? Do not do what I'm about to do. It's wrong. Okay? So I got the 2. All right. Well, it fell 2 meters. Okay. All right. No worries there. Okay? And my acceleration is negative 9.8 meters per second squared. Now, this whole thing is underneath the radical. It just isn't the top part. The whole thing's underneath the radical. Why is, as it is written, okay, I realize that sounds fairly, biblical. As it is written, why is this going to create problems? Brett?
Because it fell in it went in negative 2 meters.
Oh, no. Beyond that. I have a negative underneath the radical, right?
Mm-hmm.
Okay?
Oh, yeah, that creates imaginary numbers.
Oh, that creates imaginary numbers, okay? So this would be imaginary time, which if we're at Disney World, that's cool, okay? Right? Oh, it's imaginary time. No, okay? We can't have imaginary time. So there's a couple of things that you can do. You can sit here and go, okay, well, that's simple. Oh, I'll just make that positive. Okay, easy peasy. There we go. No, you can't change the parameters of the system. Down is always negative. It's a simple fix, but it's wrong. That has to remain as a negative value. But here's the beauty of this. If we're defining down as being negative, guess what? This becomes
Negative.
and -2. Now I have two negatives underneath the radical, which makes it
Positive.
positive. Okay?
So initially I was correct, right?
Yes.
I was right initially.
You were right. I just
Okay.
wanted to go one.
Gotcha.
Yeah.
Okay, good.
Okay, so somebody take 4 divided by
I mean, that's
9.8, and
something.
here's the other thing that you're going to forget to do.
Thank you.
Trust me. You're going to forget to do all of this, and you're going to forget to take the square root. Okay? What'd you get? 0.63 seconds. 0.64? Actually, I can have 3 significant digits. 0.639 seconds. Okay? Now, so 2 meters is about like here, right? So I let go of it. 1 Mississippi. All right? So I didn't quite get a whole Mississippi, right? So I got about 0.639 Mississippis. All right? Okay? It's a good timing device. Okay. So we're good. So now if we go back and look at our velocity time graph, now we know that this time is 0.639 seconds. Now, here's what I want you to do before you even do the calculation. When it hits, is my velocity at the point of impact going to be bigger than negative 9.8 meters per second, smaller than negative 9.8 meters per second, or equal to negative 9.8 meters per second? Ms. McIntyre. Take a stab. Restab.
Oh, bigger. Is it going to be bigger?
Bigger.
Bigger? Yeah. No.
Miss McIntyre.
Yeah.
Remember, this is your acceleration, right? This is the rate at which your velocity changes. Okay? So, what this means is that if you fell for exactly 1 second, at the end of 1 second, you would be traveling negative 9.8 meters per second. Okay? Is my time less than a second? So my velocity has to be less than negative 9.8. Okay? If I fell for like 1.2 seconds, then my velocity would be greater than negative 9.8. Okay? So since I know I fell for less than a second, my velocity at impact has to be less than negative 9.8. Makes sense? Okay? All right, so we're cool. So now we need to find the velocity at impact. So what can I do there? Okay? So one option is, and there's a couple of things, there's a couple of ways you can do this problem. I'm going to show you both ways. It's a personal preference thing. Okay? So I need that velocity at impact. So one option is that I can simply go, oh, I know it falls for 0.639 seconds. And I know that V equals V naught plus AT. Right? What's my initial velocity?
0.
0, because I'm dropping. Do I know my acceleration?
Yeah.
Negative 9.8 meters per second squared. Do I know my time?
Yep.
Yeah. So one option is that I'm going to take 0 plus negative 9.8 meters per second squared, multiply that by the time of 0.639 seconds. So somebody take negative 9.8 times 0.639.
Negative 6.26.
Negative 6.26 meters per second. Okay? So you could run this fast. Okay? This isn't like I'm breaking the sound barrier. All right? It's only falling, 2 meters. So it isn't going that fast when it hits the ground. Okay? I don't recommend that you jump from 2 meters because, it's going to be fairly fast when you hit the ground. But this isn't like warp speed. Okay? Now, this is one way to do this to get your velocity. And if you like that, go with it. It's lovely. Okay? It's beautiful. But what's the downfall to this, doing it this way? There's a downfall to this.
If you mess up on the seconds, then
Beautiful.
they're on
If I've dinked up my time calculation, this now is wrong. Okay? Like if I forgot to take the square root here, this now becomes wrong. So, is there a way that I can find the final velocity without using time? If I go to that equation, oh, let's talk about that equation. I like that equation. So I've got v squared equals v naught squared plus 2ax. True? What's my initial velocity?
0.
0. So I'm going to take the square root of this. So I'm going to take 2 times, and again, I'm going to do this wrong. So wrong. So now, again, what's the problem if I do this?
You're going to have an imaginary number.
I'm going to have an imaginary number. But if I make this
Negative.
negative, okay? Now, this is where your calculator will lie to you. Okay, not necessarily lie to you, but it won't give you the whole picture. So, do this, and you should get something close to what we just got. What'd you get?
6.26.
6.26? Okay. Now, here's the problem. This is what your calculator tells you the velocity is a 6.26. Here's the disadvantage of this equation. Because if you write down 6.26, what does that indicate in terms of direction? It's positive. So if you write that down in terms of a velocity, you're saying, I'm going to drop the ball, it's going to fall, but at the point of impact, it's actually going up with a velocity of 6.26 meters per second.
That's so confusing.
Kind of weird.
That's so confusing.
But what's the square root of 4?
2.
Or negative 2.
Yeah.
So any square root has 2 possible roots, right? So what do you have to do? Yeah, you just have to choose the negative root. There you go. Okay? Which is completely legal within the realm of mathematics. It isn't like I did something geeky here. Okay? Oh, I'll just randomly choose negative. No. I can do that because there's 2 possible roots. Okay? Good so far. Got it, Grant? Okay, stop that for a second. Stand up. Okay. So, now here's the other version of the problem. The beauty of all gravitational problems is that basically boil down to one of 2 things. You either drop it or you throw it up in the air. That's basically it. Okay? So now, I want to change it up. I'm going to take the ball and I'm going to throw it up with an initial velocity of 12 meters per second. Right? That's the only number that I know, is 12 meters per second. From that one number, from that one sole number, I want to figure the time up, the time down, the maximum height. I want to know how high it is and the velocity at 1 second, and how high it is and the velocity at 2 seconds. Okay? I want to do all of that from one number. Okay? Now, let's chit chat. Even though I don't ask you to, let's start with the velocity time graph. What's the velocity time graph going to look like?
And it's going to be like that.
It's going to start at
Positive.
12, and it's going to do what?
It's going to go down.
Dink. Like this? Right?
I think so.
I think so. So at this point, what's the velocity? So where's the ball?
Of max and height.
Max height. So at this point, the velocity is 0, and it's at its max height. Ooh, that's nice. Okay, that's nice.
Time up,
Now,
time down.
before we do any calculations at all, okay, before we do any calculations, here's my question. Maddie, okay, you ready? Okay, I like that. Is it going to take more than 1 second, less than 1 second, or exactly 1 second for the ball to reach its maximum height? Yes? False. What did you say? Less than 1 second. Why? Well, then riddle me this, Maddie. What's the slope of this line? No, that's where it starts. 12 meters per second is the point where it starts.
It's okay.
What's the slope of the line? Oh, beautiful. So the slope of the line is negative 9.8 meters per second squared. Right? Because that's my acceleration caused by gravity. So, Maddie, riddle me this. If I started at exactly 9.8 meters per second, how long would it take to get to 0? One second. Okay, because that's what it means. Because if I started at exactly 9.8, for every second that goes by, my velocity drops 9.8, right? So if I started exactly 9.8, it would take me exactly 1 second to go to 0. So if I'm starting above 9.8, it's going to take me more than 1 second. Seem reasonable, okay? If I started at 6, my time would be less than a second, right? So here's what's important about this gravitational acceleration. Every second that goes by, one of two things is going to happen. It's either going to be going 9.8 meters per second faster or 9.8 meters per second slower for every second that goes by. That's what it means, okay? Now, if the Earth was a little bit more massive, this would be easier and g would be negative 10. It would make the math a lot easier if g was negative 10. So then we'd go, oh, it would take, we'd start at 10, it would take 1 second to go to 0. We got a slightly smaller rock than what we wanted. We had to settle for negative 9.8, okay? All right, so I know my time up is going to be a little bit more than a second because I started a little bit faster than 9.8 meters per second. Okay, that's cool. Now, one of the things you're going to have to be able to do is draw vector diagrams that shows velocity. So this, if you were to draw the vector diagrams, you'd say, okay, here's V1, right? So you're going to start with a certain velocity. As it goes up, what's going to happen to the magnitude of this velocity vector?
It's going to shrink.
It's going to become smaller, right? So here would be like V2, and then here would be like V3, right? Is it accelerating on the way up? Yes. What's the direction of the acceleration? Down. So you can say, okay, here's my acceleration vector. I don't care what it is, it's pointing down. Now, at this point, we're at maximum height, right? We're at 0. Once it starts to fall back down, what happens to the direction of my velocity vectors? They flip over and start pointing down. So here would be V1, then they're going to get bigger, right? V2. V3. So if I ask you to draw velocity vectors, this is what I'm looking for. Now, here's the kicker. What's the acceleration on the way down? Does it still point downward? Mm-hmm. So does it have the same acceleration going up as it does going down? Mm-hmm. Yeah, and you can tell that. Why? Because we've got the exact same slope on velocity time graph. Okay? Now, you go to the Jedi-Stoffelwa thing. If I'm going to throw the ball up in the air, okay, right? As soon as it leaves my hand, I stop applying a force, right? I don't apply force anymore. So if I threw this, and I stop applying this force, and there's no gravity, what would the ball do? It would just keep going straight up at a constant speed. But if I stop applying the force, and I get a different acceleration, that means there has to be a different force acting on it. Because when I'm throwing it, I have to have a positive acceleration to make it speed up. But as soon as I stop applying that force, a different force kicks in, and I get a different acceleration. Okay? So anytime you have a different acceleration, you have to have a different force, right? Because force equals mass times acceleration. So if I ever change my acceleration, I can only do that by changing the force. Okay. So now that we've got the big idea, what's the position time graph going to look like?
It's going to be near. Yep.
That?
No.
Bad. It's bad. Okay? Whoop. Like that? Why? Okay, gravity is slowing it down, velocity is changing. Now, here's an interesting question. At time 0, what would the slope of the tangent line be? No.
0.
No.
Wow.
Because that's how fast it's going at time 0, right? Oh. At this point, the slope of the tangent line would be what?
0.
Because the velocity is? Because it's? And
Max
because
height.
it's?
Max height.
Stop to? Change direction. Thank you very much. Okay. That was painful. All right. So, am I slowing down on the way up?
Yes.
Am I speeding up on the way down?
Yes.
Okay. I changed direction. It meets the 3 criteria, right? Life's good. I can also meet it here. Oh, look, I'm slowing down. I'm approaching 0. And then I start to speed up after I get past 0. Okay, well, that's good. All right, so now we can start to do math. I need to get the time up. So, do I know my initial velocity on the way up?
Yes.
Do I know my final velocity on the way up?
Yes.
Do I know an acceleration?
Yes.
Yes. So what relates velocity final, velocity initial, acceleration, and time?
The first one.
The first one. Frankie, the first one. Okay. So, we know that V equals V naught plus AT. What's the first thing that you're going to do? Solve for time. So I'm going to have V minus V naught over A is going to equal time. Now, this is what you're going to do wrong. Do not do what I'm going to do. Going, oh, okay, well, that's 12 meters per second. And my acceleration's negative 9.8 meters per second squared. What's the problem?
There was a negative.
I'm going to have negative time, which is kind of weird. Okay? That does happen on really bad days, but this isn't one of those situations. So, what can I do?
It's supposed to be.
Just randomly make it negative?
Yes.
No!
It's 0 minus
0
12.
Ah, it's 0 minus 12. Now, that fits. Okay? Now it becomes consistent. So somebody take 12 and divide it by 9.8. What's it? 1.22 seconds. All right, so that's my time up. Now, on a gut feeling, if it takes 1.22 seconds to go up and it returns back to the same height, how long do you think it's going to take to go down?
1.2.
1.22 seconds. And you can do that as long as it returns back to the same point. But only if it returns back to the same height. Because if I throw it up in the air, okay, and I don't catch it, right?
That was weird.
That was weird.
I don't mean to brag. But it hit the edge of the carpet. I couldn't do that again after trying. It literally hit the edge of this carpet and it went, me. Okay, so where'd my ball go? Well, I can't teach without it.
Gravity storm.
Gravity storm. Well, that was a carpet storm. Okay, back again. All right, we're back. All right. So, I don't want people pretty burdened with that. Oh my God, we lost the teacher. He's back. It's okay. All right. So here's what we've got on our velocity time graph. So we started here at 12 meters per second. We're here at 1.22. So this is going to be out here at
2.44.
2.44. Now, what do you think the velocity is? What do you think the velocity is at impact? No. Negative 12. Why? Yes. So it lands at negative 12 meters per second. Now, what speed does it have when it lands? No. No, you're making this difficult. Don't.
Okay.
Negative 12.
No, speed. Speed is a scalar quantity. It's just a number. It's 12. Yes, it's 12. So it leaves with the speed of 12. It lands with the speed of 12. Okay? Velocity is 12 and negative 12. Okay? Huh? Yes, it would be. And that's why the speed is the same in both situations. Okay? All right. So we got this done. So we got time up, we got time down, total time, boom, we're golden. Okay? So the next thing we want to do is we're going to find the maximum height. Now, This has an identity crisis because there's a whole bunch of different ways you can find the maximum height. This is a personal preference thing. Okay? Could I use my velocity time graph to find the maximum height?
Yeah.
Yes, what would I do?
Find the displacement.
Yeah, I find this area. Okay? This area would represent my maximum height. I know my height, I know my base. Grace, how do you find the area of the triangle?
1/2 base times height.
Bingo. So I can do 1/2 base times height. But again, what's the downfall? If this time is wrong, that maximum height is going to be wrong. It works, and this would be lovely as long as the time is right. Is there a way that I can find the maximum height that doesn't involve time? That equation. Okay? So one option to find the maximum height. Okay? Here's another option. Is that you can use v squared equals v naught squared plus 2ax. You know the final velocity? Which is going to be? No. It's 0 at maximum height. Right? Do you know the initial velocity? Yes. Do you know the acceleration? Yes. Well, it's the only thing you don't know. X. So now, here's what's important. Okay? This is why this is so important that this plays out like this. Because my final velocity is going to be 0. Now, that's going to be, and this is important, where you put these brackets in terms of squaring it. We're not squaring a negative 12. It's 0 minus 12 squared. Okay? Then I'm going to divide by 2 and negative 9.8 meters per second squared. What should my value of x be? Positive or negative?
Positive.
Positive. And that's what's going to happen because I'm going to have a negative number on top and a negative number on the bottom, which is going to produce that positive value for my maximum height. Okay? This is an option. It's lovely. Okay? The beauty of this is you go off of known values. You're not dependent upon time. Home run deal. Here's a third option that you can do to find the maximum height. But wait, there's more. There's 3. For an additional shipping and handling, I'll throw in another equation. It's a bargain. All right. Could I use this equation to find the maximum height?
Yeah.
Yes, I could. Do I know my acceleration?
Yes, sir.
Now, but here's the kicker. What value of time do I use? No. If I put in 0 for time, what am I going to get?
0.
0. 1.22, why? Yeah, that's when it said it's maximum height, right? Okay? So I can do this. I can go 1/2 negative 9.8 meters per second squared times 1.22 seconds squared plus 12 meters per second times 1.22 seconds. So this we will use this later on. This is a beautiful equation. It's like a function equation. It gives you height as a function of time. But here's what you have to be very, 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 very careful of. This has to be a negative 9.8 meters per second squared. Otherwise, you're adding 2 positive numbers together and you're going to get a height that's way, way too big. Okay? So this is a lovely equation. It's grand. You got the 12 meters per second. Boom. There you go. Okay? It's lovely. It works. Fantastic. So anyway, so somebody find me, that no matter what, somebody give me a number. Through one of the 3 processes.
7.35.
What'd you get?
7.35.
7.335
35. Yeah.
meters. Okay? Now, this ceiling is about 2.5 meters tall. So this would be about roughly, 2 times as high as this ceiling. So that's a pretty good shot. Okay? So that's 7.35 meters. So no matter what, you're basically going to get the same answer. There might be a little bit of difference in rounding, but you're basically going to get 7.35 meters. Okay, so that's cool. So we've got the maximum height, the time up, the time down, all this good stuff. Now, one of the things I want to do is I want to find out how high it is and how fast it's going at exactly 1 second. And then I want to find out how high it is and what the velocity is at 2 seconds. Okay? So, if you go to this velocity time graph, I want to figure out how fast it's going at this point. Now, at 1 second, is my velocity going to be a positive or negative number? Why?
Because it takes 1.22 seconds.
Yeah. It takes me 1.22 seconds to reach the maximum height. So at 1 second, I'm still on my way up. This is the slope-intercept thing. The only way to do this at the 1 second is to use the V equals V naught plus AT. Do you know the time? 1 second. Do you know the acceleration? Yes. Do you know your initial velocity? So this is the only way you can find that velocity. This is it. This is the only way you can find that velocity. Now, to find the height at 1 second, there is only one way you can do this. Only one way. You do not have another. You do not have a choice. The only way that you can find that height at 1 second is to do the x equals 1/2 AT squared plus V naught time. This is the only thing. This is the only way you can find this because it's a function equation. So you got negative 9.8 meters per second squared. You have the time of 12 meters per second is your initial velocity. You plug in 1 second here. Now, think about this. At 1 second, okay, at 1 second, what does my height have to be less than at 1 second? Why does it have to be less than 7.35? That's my maximum height. So at 7.35 seconds, or at 7.35 meters, that's my maximum height. So I know when I put in these numbers, I have to get a number less than 7.35. If I get something above 7.35, I've done something wrong. Okay? Makes sense. Then the same thing is going to happen here. The only thing that happens here is that this becomes 2 seconds. Now, at 2 seconds, think this through. Miss Wright. At 2 seconds, what should the sign of my velocity be? Why? I'm on my way down. At 2 seconds, I'm over here in the negative nether region. Okay? I've gone to the underworld. So my velocity is going to be negative. Okay? Is my height at 2 seconds going to be a negative number? Aubrey? Yes or no?
No.
Why?
Because, I mean, you're just coming back down. You've already been. Like,
That's right, I'm coming back down, so...
it's less than your max height. So.
Yeah, but I'm still above the ground,
Yeah,
right?
like, you're not.
So I go from here, I go up. I am on my way down, but I'm still above where I started. Okay? So you get a problem like this is the only thing you do. On this, to get a velocity or a position at any point in time, this is the only thing that you can do. That's it, nothing else. Okay, stop that. Okay, now, on this one, when you 1 through 5, even though we've talked about gravity, 1 through 5 has nothing to do with gravity. Okay? So do not use G. Gravity storm?
Yep.
Okay. On 1 through 5, do not use G. Now, let's talk about number 6. So I'm going to drop a rock from on the bridge, draw a motion diagram showing at least 2 velocity vectors and an acceleration vector. So I'm going to hold the rock up, I'm going to drop it, boom. So ignoring air and friction, or determine how fast the drop ball will travel at the end of 1 second, 2 seconds, 3 seconds, and 4 seconds. So I'm going to hold it up here, I'm going to drop it. I want to know how fast it's going at 1 second, 2 seconds, 3 seconds, 4 seconds. Then I want to know how far the rock has traveled at the end of each time. Here's the deal. The only way that you can figure out how far it's traveled at the end of each time is to go to this equation here. X equals 1/2 AT squared plus V naught time. When you drop it, what's your initial velocity? So this whole thing goes away, right? Do you know your acceleration? Do you know your time?
Yes.
Yeah, 1 second, 2 seconds, 3 seconds, 4 seconds. So you're just going to use this equation to figure out how far it's traveled. Now, eventually you're going to have to draw a position time graph and a velocity time graph so that everybody's drawing the same graph. Here's the bridge, okay? We're going to make the bridge be 0 meters, okay? So everything is going to be negative values down here because it's falling away from 0 and it's going down. And you'll see that you get negative numbers out of this calculation because you've got a negative 9.8 meters per second squared multiplied by a time squared. So that way your position time graph is going to start at 0, but then you're going to have negative numbers from that. Okay? Keep that in mind. When you get to number 15, you're going to launch a mortar straight up. How high is the mortar at this point? The only way you can figure out how high that mortar is to use this equation, because again, you know your acceleration, you know your initial velocity, and I've given you the time. So on 15A, this is the only way you can do that equation. That's it. There's nothing else you can do. That's the only way that you can find it. What's the velocity of the mortar? Is it on its way up or is it on its way down? Okay, I'm done. You're on your own.